This is a short video to show how to write code to run a simple confirmatory factor analysis in Mplus. So we're using the same basic model that we were talking about for path analysis and that we're going to use for our hybrid model in class next week. So we have data on particular items that measure self-perceptions, goal valuation, and motivation self-regulation. So for this example, we're going to imagine that we have 3 factors. Each factor is measured by 3 indicators, and those indicators are actually named on the variable command. So let's start talking through this. So you can see I gave a title here, CFA Model 1. The data, I just say file is sasr_2013.dat. That is where my data are housed. And then in the variable command, I need to say names are, and I need to give names for each of my variables. Now here, I've given the names S08, S11, S13, S15, S20, S25, S26, S29, and S35, because those are actually the names of the 9 items on the SAS scale. So we have actually 3 items for each of the 3 factors. So in the model command, I'm going to tell Mplus which factors are measured by which items. And so now we see a new command in Mplus. That's the by command. By is short for measured by. Remember, we talked about on last time. On is short for regressed on. By is short for measured by. So on the left-hand side of the line, we'll have the name of the factor. And so I've called the self-perceptions factor self-P here. Self-P by, so self-P is measured by S20, S13, and S11. So self-P by S20, S13, S11, semicolon, because it's the end of the line. And so this means the factors measured by those 3 indicators. Now, by default, Mplus is going to use the marker variable strategy for identifying latent variables. And what that means is that the very first item or indicator that you list will become the marker variable. So here, S20 is actually the marker variable because it's the first indicator that I mentioned. So a really easy way to change the marker variable is just to change the order in which you mention the items. You could use the fixed factor variance strategy. If you want to do that, you can set the factor variance for the self-perceptions factor at 1. But for right now, we're going to use the marker variable strategy. So I don't really have to say anything about what my marker variable is. Just remember that the first variable that you list after by will become the marker variable. So if you have a strong feeling about which marker variable or which variable you want to use as a marker variable, just make sure that that one is listed first. So that's the first factor. The second factor is goal valuation. I call goal valuation goal V. Goal V is measured by S15, S29, and S25. Here, S15 is going to be the marker variable. And again, don't forget to end the line with a semicolon. And finally, motivation self-regulation. That factor I've called MOT-S-Reg. And MOT-S-Reg is measured by S26, which will be the marker variable, S08, and S35. And again, I end with a semicolon. Now, one important thing is you can name a factor anything you want because it's a latent variable. There's only one important thing you cannot do. You cannot name a factor something that already, the same name as a variable that you're already using, right? So I can name my factor anything except for those S08, S11, S13, S15. So you can't have a factor name actually be the same as a variable name, but that's really easy to control because remember, we're telling the variable names from the get-go. So you have total control over that. Okay, and then in the output, I'm asking for sample statistics, that's samp stat, residuals, that's residual, STDYX is going to give me my standardized results, and then I just put in here mod indices 4, which will produce some modification indices. So now if I click on run, then you should be able to see my output, I hope. So here's my output file, and you can see that the first thing that happens in the output is that we just see the input instructions again, which is nice. Then we want to see this nice line, input reading terminated normally. That means that everything was read normally from that input file. And then I get a basic summary. I have, again, 619 observations. I have 9 variables. My 9 observed variables are all endogenous variables because they're all predicted by a factor, right? And then I get some information about the analysis, and then I get my sample statistics. So you can see the means on each of these 9 variables. They are in the 5s and 6s. These variables are all on a Likert scale, by the way, and I think the range is from 1 to 7. So you can see actually, for example, S25 and S29, those means are actually quite high for being on a 7-point scale, but I digress. Then we have the covariances, and then finally our correlations, which are certainly much easier to look at than covariances. Then we get a nice table of the univariate sample statistics. Then the next line that we really want to see is that the model estimation terminated normally. That is good. And then we get our model fit information. So we can see here that the chi-square test of model fit is 37.357 with 24 degrees of freedom. And the p-value for that chi-square is 0.0403. So that means that the chi-square is statistically significant, which means that there is a statistically significant difference between the model implied variance covariance and the population variance covariance. However, you can see that that's, the p-value is 0.04, so it is statistically significant, but just barely so. And now when we look at, and remember that the chi-square is going to be influenced by sample size. So when we have a large sample size, we have lots of power to detect even very, very small deviations between the model implied variance covariance matrix and the variance covariance matrix. So we also look at measures of model fit, which we'll be talking about in class. And you can see the RMSEA is 0.03, the CFI is 0.995, the TLI is 0.992. Those all actually indicate pretty decent model fit, and the SRMR is 0.02. So actually our model fit indices look pretty good. Here are our unstandardized factor loadings or pattern coefficients, and you can see that we don't actually get a test of statistical significance for the 3 marker variables, 1 per factor. The estimate of the unstandardized coefficient for each of the marker variables is always going to be 1. But we do, and so that's why these two-tailed p-values are 999, because we're not actually estimating those. We're not actually estimating those paths. However, we will get tests of statistical significance for the standardized coefficients. You'll see in a minute. Okay, and then here are the covariances between the 3 factors: goal valuation, motivation, self-regulation, and self-perceptions. But again, these are covariances, not correlations, so those can be difficult to actually interpret. We can see, though, that all of the covariances are statistically significantly different from 0. Okay, and now here are the variances of our factors. So we have the variance of self-perception is 1.137. The variance for goal valuation is actually the lowest, 0.647, and the variance for motivation self-regulation is 1.231. So you can see that actually there's less variance in the goal valuation factor than there is in self-perceptions or motivation self-regulation. And that actually makes sense because earlier when I was pointing to those items that had really high means, those were all actually on the goal valuation factor. So people tend to actually answer those items much more similarly to each other. They tend to, mostly endorse those items with like 6s and 7s and 5s, 6s and 7s. So you just don't get as much variance in that factor. All right, now we can look at the standardized model results. And here I can see that the factor loadings for all of my coefficients, all of my standardized factor loadings are statistically significantly different from 0. And I generally would like these to be sort of moderate to large, not just statistically significantly different from 0. And you can see that for self-perceptions, the factor loadings range from about 0.7 to 0.82. So that's nice. They're nice and high. For goal valuations, again, their goal valuation, they range from 0.76 to 0.84. For motivation self-regulation, they range from 0.72 to 0.85. So really nice, strong, healthy factor loadings. And now I can look at the correlations among my factors, and you can see that goal valuation and self-perception are the least correlated with each other of these three constructs. They're correlated at 0.46, which is, moderate correlation, right? So people who value the goals of school also tend to perceive that they're good at school. But the correlation between motivation, self-regulation with those two factors is actually quite a bit higher. So people who value the goals of school tend to be more motivated, and people who perceive themselves to be good at school also tend to be more motivated. And those correlations are pretty high, much higher than the correlation between goal valuation and self-perceptions. They're both about 0.68, which is pretty high. And here you can see that the variances now for all three of the variables are 1 because this is the standardized solution. So the standardized solution assumes that, is standardized such that the mean of each factor is 0 and the variance is 1. And because of that, then the residual variances here are actually 1 minus the R squared, or 1 minus the proportion of variance in the item that's explained by the factor. So if I scroll down, hold on, let me make this a little bigger. I hope that you can see this. If I scroll down, if you look at SO8, the R squared, which is the proportion of variance in item 8 that's explained by its factor, is 58.2%, right? 0.582. And then 1 minus 0.582 is actually 0.418. So what this means is that 58% of the variance in item 8 is explained by the factor, and about 42% of the variance in item 8 is not explained by the factor. You can see that some of the highest R squareds are, let's see, S29 and S35, where you can see for S29, actually over 75% of the variance in item 29 is explained by the factor, and just under a quarter of the variance in item 29 is left unexplained by the factor. Now we can look at our residual output, and we'll get, I scroll down, residuals. I get, actually standardized residuals are the easiest things to look at. So we can look at the standardized residuals or the normalized residuals, either or, for the covariances. And these actually are, they are in a z-score metric. So any standardized residuals that are between, -2 and 2 are considered to be fine, right? And when the standardized residuals end up outside that -2 to 2 range, that means that those standardized residuals are, statistically significantly different from 0. But again, you often have a really big covariance matrix. So if 1 or 2 of those standardized residuals out of a large number of standardized residuals ends up being, just above 2, that's not necessarily, hugely problematic, but we certainly want to look for standardized residuals that are quite large here, right? Or if we see a situation where there are lots of standardized residuals that are above 2. So when I look at this, I don't actually think that the standardized residuals here look too bad. I see a couple of standardized residuals that are above 2, but not very many, and they're not very far above 2. So, okay, I mean, it's not perfect fit, but there's nothing here that's super problematic. But now remember, the modification indices tell me how much would the chi-square drop if I were to freely estimate a parameter that's currently constrained. So if we look at our modification indices, we can see that there are 2 modification indices for buy statements. So saying, if you allowed item 11 to double load on goal valuation, that would drop the chi-square by about, and these are approximate, these chi-square drops. So it may not be exactly this when you do it, but it would drop the chi-square by about 7.7 points, okay? Or if you allowed goal S13 to double load on goal valuation, it would drop the chi-square by about 5.78 points. These are univariate tests, so if you were to actually allow both S11 and S13 to load on goal valuation, you would not necessarily expect that the chi-square would drop by 7.694 plus 5.783, right? Because you'd be sort of multivariately making 2 constraints at once. So these are always, if you were to just do this one thing, how much would you expect the chi-square to drop? And you can see in the with statements, looks like the chi-square would drop by almost 7 points if we were to allow S29 and S20 to correlate with each other. And I didn't show you what the items are, but actually this makes sense because those items, even though they're on 2 different factors, have very similar wording. And so, maybe that's what's going on. So just to kind of show you how you could actually modify confirmatory, how you could correlate errors and run a modified confirmatory factor analysis, I'm going to show you a second model where we actually build in this correlation between S29 and S20. So let me close this output file here. And now I can save this input file. I'm going to call this O2 CFA model 2, right? Revised. I guess that's kind of obvious, but save. And now in the model command, I can actually just say, I want to allow the errors of S29 and S20 to correlate with each other. So I can just type S29 with S20. Now, it looks like I'm referring to the variables here, but remember, when a variable is endogenous and you say the variable name, you're actually referring to the residual of that variable, which would either be the measurement error, in this case, or the disturbance, if it's in the structural part of the model. So saying S29 with S20 actually means allow the error of S29 to correlate with the error of S20. And again, let me just say, you don't want to just willy-nilly start making modifications. I'm doing this for pedagogical reasons, but you should think very carefully before you start correlating errors, right? But just to kind of show you how this works, I'm correlating S29 with S20. I save this, I run my model, and now interestingly, I'm going to have 1 fewer degree of freedom now, right? So now the chi-square test of model fit is 30.34, basically, with 23 degrees of freedom. And you can see now the p-value is not statistically significant, which suggests actually that the model implied variance covariance matrix is doing an adequate job reproducing the variance covariance matrix. My fit indices look a little bit better, but actually fairly similar, truthfully, because they looked pretty good before. They haven't changed that much, but they're maybe slightly better. If you look at the model results, let's go to the standardized model results, actually. You look at the standardized model results, you'll see that we still have really nice factor loadings, right? We still have very similar correlations among the factors, but what we see now is that the errors of S29 and S20 are actually slightly positively correlated with each other. What that means is that S29, so item 29 and item 20 are more correlated with each other than would be predicted by the factor structure that we've specified, which again, given that I said that there's very similar wording between the two items, that actually makes sense. So there's sort of a method effect here in that the two items have very similar wording. And now I'm sort of taking that into account by allowing these errors to correlate with each other. And so I'm getting a better fitting model. And that is it. So that's our brief demonstration of confirmatory factor analysis in Mplus. Thanks.